let me welcome our speaker of today. It's a big pleasure to have Gerald Dunne with us today. He's professor of physics at the University of Connecticut, and after, so he's Australian in origin. After his studies there, he got a PhD at Imperial College and then worked at MIT for a few years also as faculty. And the primary interest of his research is exactly what he will talk about today, although his research is very broad, but non-perturbative physics is the theme of the colloquium of today, and we're very happy to have you here, Gerald. Go ahead.
Thank you very much, Valentina, and thank you to the GGI. This colloquium series is very interesting so far, and we appreciate what you're doing. So I want to give a simple introduction to these ideas surrounding resurgence and non-perturbative physics. I'm going to keep it fairly general as it's a colloquium style and tell you some of the background. So the main motivation from my perspective is to learn something new and interesting about the Feynman path integral. Now, we're all familiar with the Feynman path integral being a very powerful computational as well as conceptual framework for studying quantum field theory and quantum mechanics. But there are also some very important physics calculations with which the path integral struggles. A very famous one, of course, is finite density problems. The finite density of the chemical potential, there's still a complex part of the action. This is generically known as the sign problem. Also, non-equilibrium physics problems using Schwinger-Keldysh contours also introduces oscillatory aspects that are difficult to control computationally for the path integral, and similarly with real-time evolution. And also quantum systems in extreme background fields suffer from these problems. So the standard computational methods derived from path integrals we're all, again, familiar with. We can regard the path integral as a generating function for perturbation theory, Feynman perturbation theory. This is extremely successful and tested to very high precision in the appropriate regimes. There's also the non-perturbative side numerically using Monte Carlo, say in lattice gauge theory, which again, for a certain set of problems is fantastically successful at particle physics calculations from first principles. We also learn a lot about non-perturbative physics from semi-classical instanton calculations with path integrals, things like instanton gas calculations. And also we can do asymptotics, taking large or small limits of certain parameters in the path integral. Now, Resurgence is a framework that seeks to actually unify these different approaches. And the underlying technical problem that motivates what I'm interested in is how can you actually compute the quantum path integral? Are there some new ideas here from Resurgence that we can take advantage of for actual computations? So again, keeping things general, the Feynman path integral gives us quantum transition amplitudes from some initial configuration to a final configuration. So in quantum mechanics, it's just a sum over all possible paths between the initial and final positions, weighted by the exponential of I times the action for each path. The natural generalization to field theory is instead of summing over paths to sum over all field configurations, again, weighted in terms of an exponential involving the action of the field configurations. So even though this is a very formal and not particularly well-defined mathematical object, we learn a lot already from this formalism. For example, we learn why classical mechanics is naturally described in terms of critical points of some action functional, which is not at all obvious why that should be the case. We also learn a simple bridge from classical field theory to quantum field theory without having to go through some Schrodinger equation type intermediary. We learn that quantum perturbation theory can be understood as just fluctuations about the trivial saddle point of this functional integral. But the action in an interacting theory goes beyond just simple quadratic terms. And so there should be other saddle points, and these are identified with non-perturbative physics. And the general feature of Resurgence and philosophy behind the Resurgence program is that these saddle points should not be independent, that they should be related by analytic continuation constraints. And the consequence of that, physical consequence of that, is that perturbative and non-perturbative physics become entwined in some way. And then the question is that, first of all, is it true? And secondly, is it useful? Can we take advantage of some structure like that? So this is an old story. It goes back a very long time. And the first discussion of these ideas underlying resurgence comes in the work of Airy and Stokes back in the 1800s. So Airy was studying the problem of rainbows, and in particular things that at those times they called spurious rainbows, but nowadays are referred to as supernumerary rainbows. These are these bands hidden behind the primary bow of a rainbow. So Airy wrote this beautiful paper in 1838 discussing the optics of caustics, and came to the conclusion that he could describe the behavior of these spurious or supernumerary rainbows in terms of a given function that we now know as the Airy function. And Airy derived an integral representation of this function, but he faced the original sign problem. It was an integral with an oscillatory integrand, and using the techniques at hand, just basic quadratures and log tables, he was only able to calculate a few terms in the expansion near the primary bow. A few years later, Miller did some experiments with artificial rainbows and was able to observe 30 of these bands. This is a modern picture thereof, but he distinguished or characterized these 30 bands. Some years later, Stokes entered this game, and he wrote a very beautiful paper where he did with a modern calculation of calculating the asymptotic expansion around infinity of this Airy function. And this was such a revolutionary calculation at the time that in Stokes' obituary, Lord Kelvin referred to this particular calculation, that with this mathematical super subtlety, Stokes solved this problem that Airy was having and was able to describe many of these bands very accurately with a very simple expression. But that was just the start. Stokes wrote an even deeper paper 7 years later, where he introduced the concept that we now refer to as the Stokes phenomenon. So here's the integral representation of the Airy function. Here's a plot of the Airy function along the real axis. We see there's this exponential decay at positive x, and there's this oscillatory behavior at negative x. And so here's the sign problem, of course. When x is large, this integrand is oscillating extremely rapidly. There are massive cancellations, and controlling those cancellations as an integral along the real axis is an impossible problem. So Airy actually struggled to produce values of this function from x plus 3 in certain steps down to about x equals minus 3. So he was able to observe this first dip, but he couldn't go any further. Well, we now know, of course, the resolution is to consider contour deformation in the complex plane. As x varies, the saddle points that dominate this calculation move. The steepest descent contours through those saddle points move and deform. And we can actually understand this better if we look at the Airy function in the complex x domain. Remember, x is the external parameter. Think of this, by the way, as a baby version of a path integral or zero-dimensional path integral. X is a parameter such as a chemical potential or a temperature or a background field. And here, if you can see along this axis, this is the real axis along here, and you see the oscillatory behavior along the negative real axis and exponential decay along the positive real axis. But the most striking feature of this image are these 2 pi over 3 sectors, where there's a complete change in the behavior of this function. So by thinking in terms of these deformed steepest descent contours, you learn that there are non-perturbative exact connection formulas relating these different sectors. So for example, if you take the asymptotic expansion of the Airy function along the positive x-axis, so the fluctuations around this exponential decay, and you naively rotate them by 2 pi over 3, you obtain the other Airy function, the exponentially growing. And so that's the exponentially growing Airy BI function. But if you do that naively, you completely miss the hidden exponentially small Airy function, which is hidden underneath this exponentially growing term here. And so the idea here is what Stokes realized is if you do this contour deformation procedure more carefully, you can keep track of both the exponentially large and exponentially small and the oscillatory terms consistently as you analytically continue in the complex plane. So the message from that is that if we need complex analysis to control even a very simple one-dimensional oscillatory integral, then maybe it's a natural idea to explore similar methods even for infinite dimensional path integrals, where we have similar problems, similar numerical problems with oscillatory behavior. So I would argue that an important goal in really understanding functional integrals, path integrals, would be to have a formulation that is able to describe computationally these sorts of Stokes transitions. And an idea is to actually use ideas from Resurgence and Resurgent trans series to develop an actual constructive and computational definition of a path integral that's useful in some of these physics problems that many of us are interested in overcoming. So that's some motivation. Now to introduce some of the terminology of Resurgent trans series. The name goes back to the work of Ecalle, a mathematician in the 1980s, but it can be traced back to earlier work of Dingle in the 1960s and all the way back to Stokes's work in the 1800s. So the first step in this is to take a perturbative series in some small parameter, which in applications is very often an asymptotic series, to generalize it to something called a trans series. And this is a very general concept that I'm not going to go into the full details, but in physics applications, it's enough to talk today about what I'll call a semi-classical trans series, or a formal expansion in some small parameter, again, very often a divergent series, not necessarily, but often, is generalized to a triple sum over these small perturbative terms, but also including exponentially small terms, and also powers of logarithms. So this single sum becomes a triple sum. And the idea of this is that whereas the formal perturbative asymptotic series just gives you some information about the function along a particular direction in the complex H bar plane, the trans series is designed to be well-defined under analytic continuation. So these exponential terms are these Stokes transitions of certain saddle points turning on and off as you analytically continue H bar in the complex plane. And the logarithms are generated by resonant interactions between different saddle points. So this is actually very well understood in the world of differential equations and integral equations, these very explicit so-called natural problems. And there are genuine theorems here about these trans series. And indeed, the different saddles are related. There's this intricate network of so-called bridge equations that can be characterized by Ecalle's alien calculus, which tell you very, very precisely how different saddle points are related to one another. It also allows you to develop exponentially improved asymptotics because we can keep these exponentially small subleading terms and attain much higher precision than just a formal series. But the main message from physics is that if there is this trans series structure, it necessarily unifies perturbative and non-perturbative physics. The word resurgence comes from also coined by Ecalle. This quote here from one of his books is that resurgent functions display at each of their singular points a behavior closely related to their behavior at the origin. Loosely speaking, these functions resurrect or surge up in a slightly different guise, as it were, at their singularities. So this picture is a cartoon image. Think of the raindrops as certain special singular points or saddle points or critical points or just expansion points. And the ripples, the local fluctuations around these special points. And the general idea is that these fluctuations and these saddle points are related by a network of relations, so they're not independent of one another. And the conjecture is that this structure is extremely general. So as physicists, people in quantum field theory, the main question is this sufficiently general to apply to path integrals that appear in quantum field theory models? Another important background is the work of Dingle, who has this extremely beautiful book. If anybody's interested in learning more about asymptotic expansions, I strongly recommend reading this book. It's extremely deep and very readable. And here is a quote from the obituary of Dingle by Michael Berry and John Cornwell. Before Dingle, almost every scientist who encountered a divergent series regarded it as meaningful only up to some inherent vagueness. Dingle, however, regarded a divergent series as an exact coding of the function it represents. And decoding such series is exact in principle, and in practice can lead to vastly improved approximations. And this book explains various strategies for doing this decoding. And so I borrowed this word decoding in the title of this colloquium. So a simple example of this is from these exponential integrals. So this goes back to the work of Dingle's, but is also very explicitly explained in this paper of Berry and Howells in early 90s. So imagine you've got a one-dimensional exponential integral with some function in the exponent that has at least two different saddle points. And this is the integral of this exponential along the steepest descent contour through one of those saddle points. Let's label it by n. So this is a completely well-defined integral. There are many ways to calculate it, numerically, asymptotically. The leading contribution is just the exponential evaluated at the saddle point. The Gaussian fluctuations give you some prefactor, but there, of course, is a formal series of fluctuations around that. And I label it by n because this is all tied to the steepest descent contour through that particular saddle point. And so this is some formal expansion. No big surprise, it's also asymptotic. But there's a generic feature. If there's another saddle point, neighboring saddle point, with its steepest descent contour through it, then just with relatively simple complex analysis, you can show that the large order behavior of these fluctuation coefficients around this saddle point are tied to the low order fluctuation coefficients around the neighboring saddle point. So the large order growth, R here is the order of this perturbative expansion in the fluctuation. First of all, it's factorial. Secondly, there are plus and minus signs according to particular orientation. Then there's a power, and the power is the difference between the function at these two saddle points. But the more interesting thing is that the coefficient of this leading factorial growth of the fluctuations around here is determined by the lowest coefficient around here. And then the subleading, the R-2 factorial subleading growth is characterized with a coefficient that's the second coefficient of the fluctuation around here, and so on. So this is a very explicit, universal, and in fact generic property of exponential integrals. So that's very formal. Let's look at an example. Let's go back to the Airy function. The Airy function has one of these types of exponential integral representations. The exponent is cubic, so there are two saddle points. It's a very easy calculation to work out the explicit coefficients of the fluctuations around each of the two saddle points. I labeled them here just by plus or minus. And indeed, there's factorial growth. There are two factorials in the numerator, one in the denominator. And here are the first few coefficients at low order. But given this explicit expression, it's very easy to study the large order, large R growth. And indeed, there is a factorial. There's the power. This power is 4/3. 4/3 is 2/3 minus 2/3. It's the difference of the two actions for these two different saddles. And if you look even at the subleading factorial growth, the R-2 factorial, R-3 factorial growth, you see indeed that the coefficients are the coefficients from the other saddle. So this is a generic large order, low order resurgence relation. We'll see many examples of this throughout the talk. Remarkable fact is this type of resurgent large order, lower behavior has been seen in many examples in matrix models, in quantum mechanics, in quantum field theory, and some string theory models, where it's not so obvious that this should be occurring because these are coming from either very high order multidimensional integrals or infinite dimensional integrals. And the most natural way to explain the origin of this is in terms of some sort of analytic continuation of the functional integral itself. Now, even going from this one-dimensional Airy type integral to two dimensions, even that is an interesting step. And this goes back to work of Pham in the 60s, and there's a very nice explicit description of this by Chris Howells in the late 90s. So here's a picture of what's called a Lefschetz thimble. The problem here is that you've now got a multidimensional integral, but there's only a point. The saddle point is a point. And what happens is that in this asymptotic limit, this multidimensional integral wraps itself around this saddle point here. And then there are these so-called vanishing cycles transverse to this direction. The basic problem is that in the one-dimensional case, you can think of this in terms of just changing variable from the one integration variable to the action variable, and then the Jacobian, the singularities of the Jacobian tell you all the non-perturbative structure. But now in multi-dimensions, you're trading a multi-dimensional integral for just an integral over one action. And that's why that's the basic origin of this thimble-like structure. But we can just proceed and boldly jump ahead to try and think about this in infinite dimensions and ask the question, is there any possibility of making sense of an infinite dimensional functional integral as a decomposition in terms of so-called Lefschetz thimbles, which are these functional steepest descent contours? And in principle, if we could deform to one of these steepest descent contours, the integral would be well-defined and computable. The reason for that is that a steepest descent contour, we can think of it as defining a contour where the imaginary part of the thing in the exponent remains fixed. If that's true, then in principle, we can extract that phase, and we're left with a well-defined integral with a real factor that can be used as a probability density. And so even though there's a complex Jacobian there, the main oscillatory behavior inside the exponential has been removed into this overall phase. How would you generate this in a functional integral? We can use a complexified gradient flow where you, first of all, complexify the field, the integration variables, these fields. You introduce a flow time tau and a flow equation where this flow variation is given in terms of the complex conjugate of the variation of the action with respect to the field. This complex gradient flow is designed to keep the complex part of, the imaginary part of this thing in the exponent fixed. Now, the most interesting part of, and most difficult part of this formula, even if you could develop algorithms to satisfy this complex gradient flow equation, the most difficult part of this questionable expression is the Stokes phenomenon of knowing which thimbles will contribute to the particular computation of your particular observable in your functional integral, and realizing that that thimble structure will change as you vary the parameters within the action, such as a chemical potential or some mass or a coupling. But actually, this has been remarkably successful. There already, many years ago, there were several groups who have started applying this in lattice gauge theory, and there are several examples where, using these basic ideas from thimbles, they're able to study problems with a sign problem and numerically control the sign problem to the point, to a level where they're able to implement Monte Carlo calculations. This has been developed by many groups. I'm only going to mention a couple of things here. This is now a big enterprise amongst several groups in lattice gauge theory, and things are developing rather rapidly, which is very encouraging. So here's an example of a phase transition in the 2D Turing model. So this is an interesting, non-trivial quantum field theory. Has a sign problem in a non-zero density. And this work by this group of Alexander et al. Developed a thimble algorithm where they would actually control the cost of solving the gradient flow problem with the cost of the sign problem by actually not necessarily flowing all the way to an exact thimble, but even an approximate thimble might be enough to control the sign problem enough to be able to do to a manageable level. So here's a demonstration from their work that they're able to see a phase transition in this Turing model. In fact, a demonstration of the so-called silver blaze phenomenon at low temperatures in these interacting fermion systems. So inspired by some successes like that, we can ask the question again, is it possible to develop an understanding of resurgence in these infinite dimensional path integrals? So one thing we know about path integrals is we can use it to generate perturbation theory, and we know that perturbation theory works very well. It's extremely precise in the appropriate regime. But it's also generically divergent, and also it's only part of the story. We also know that there is generically non-perturbative physics in quantum field theories. So resurgence, on the other hand, tells you that there should be some non-perturbative information encoded in that perturbation theory. So you can imagine taking a path integral, using it as a generating function to develop perturbation theory, which may be generically divergent. So it has to be controlled and regulated somehow, for example, using Borel transforms. And that will now generate a trans series through the different singularities of the Borel transform. Alternatively, you could view the path integral as a generator of a saddle expansion and develop asymptotics for those different saddles. And again, one would end up with a trans series structure. Alternatively, you could regard the path integrals through some numerical scheme, such as I just described, to develop Lefschetz thimbles and use Monte Carlo to study. And again, one would develop a trans series expansion. And the main conjecture that if we claim to really understand path integrals, these should all be the same thing. And moreover, there should be resurgence relations relating the different sectors of the trans series. And also there should be identifiable relations between the resulting trans series from these three different computational procedures. So about the divergence of perturbation theory, there's this, we're all familiar, I think, with this famous paper of Dyson, where he gave this very beautiful, simple physical argument for why we might expect that perturbation theory would be divergent. So in QED, you could imagine calculating something such as the anomalous magnetic moment of the electron. The result comes out as an expansion in the fine structure constant, which is essentially an expansion in E squared. And then Dyson argued, well, if this were convergent, then that means that there's some non-zero radius of convergence in the E squared plane, in which one should be able to freely analytically continue without hitting any major obstacles. And then he argued that that actually shouldn't be true because there should be an inherent instability when E squared is continued to negative real values. And that the natural explanation of how to get around this obstacle would be that there should be a branch cut along the negative real axis. And so this introduces the motivation for studying something like Borel summation, which is a physical regularization of divergence series. So if the typical divergence is some sort of factorial divergence, the Borel transform is a simple operation of factoring out this overall factorial growth and resulting with a Borel transform in this Borel transform variable t, which now has a finite radius of convergence. And then order by order, term by term, formally, this integral over t reproduces factorials which cancel these and reintroduces the powers of g. And so you go back again. Now, order by order, of course, you don't learn anything. You've just rewritten the expression. But if you can gain information about the singularity structure of this function by studying its radius of convergence and beyond, then you've learned something about the singularities in this Borel transform function, which can tell you now about something about the non-perturbative aspects of this function you're trying to calculate. So the singularities of the Borel transform really are the non-perturbative physics. For example, if there happened to be a singularity on the positive real t-axis, that would contribute an exponentially small imaginary part to the Borel sum. Yeah. And there's very simple examples of these in quantum mechanics that we're all familiar with, the Zeeman effect and the Stark effect. Imagine introducing an atom to a constant magnetic field or a constant electric field. This is a low order calculation that we've all done and we've all taught in our classes. But if you look at high orders of this perturbation problem, you learn that the coefficients of the expansion in powers of b squared, or electric field squared here, grow like 2n factorial. And in the magnetic field case, they alternate in sign, and the electric field case, they don't alternate in sign. Correspondingly, the Borel singularities here are on the negative Borel axis. And so the Borel integral produces real energy shifts for the electrons in the atom once it's in the presence of this magnetic field. However, with an electric field, two things happen. First of all, the non-alternating character here tells you that the Borel singularities are on the positive Borel axis. And this means that in addition to the real Stark shifts of the energy levels of the electrons, there's another physical effect, which is ionization, which shows up as a small, exponentially small imaginary part in the energy of the electrons in this atom. So now, when you come to these, when we come to learn about instanton physics, the classic problems are the double well problem and the periodic potential problem. And we learned that the exponentially small splitting these bound levels or these bound levels into bands can be characterized by instantons, which describe tunneling between neighboring wells in these potentials. What's maybe less familiar to people is that if you actually were to do perturbation theory in one of these wells, here or here, these are essentially harmonic wells near the bottom. Perturbation theory here is divergent. That's not surprising, but it's actually non-alternating divergent, and yet these systems are completely stable. So this is a puzzle, and the resolution is, there's a very beautiful resolution to this, is that the trans series actually encodes explicit imaginary terms which cancel the imaginary terms that come from this Borel summation. So here's a very explicit calculation for the hydrogen molecule ions. We've got 2 hydrogen nuclei and 1 electron. It's a double well system characterized by the distance between the nuclei. And you can calculate the energy of the electron as a series in inverse powers of this separation parameter. And there's some formal series here that you can calculate many, many terms of. And then you can calculate the effect of tunneling, the splitting between these low-lying levels. But then you can go higher orders to the second instanton order and beyond. And at second order, there is indeed a fluctuation series, but we see for the first time log terms, and we also see an imaginary exponentially small term. And these terms, what they do is that they cancel the imaginary exponentially small terms coming from the Borel summation of this non-alternating factorially divergent series. And from the theory of resurgence, you can see that these cancellations will carry on to all orders of this trans series. Now, for this to happen, there absolutely have to be very explicit relations between these coefficients and these coefficients. Otherwise, these cancellations simply won't happen. And so this is a very beautiful illustration of the power of these trans series. But in fact, it's even deeper than that. If you look again at these particular models here, so this is work originally done by Gabriel Alvarez, who was actually motivated to try and understand these atomic physics calculations by looking at simple oscillator models like the double well or the cubic potential, and then later rediscovered by myself and Unsol, and then generalized to the periodic potential. And now we understand there's a whole class of quantum mechanical systems displaying this phenomenon. So if we think of the trans series for the energy levels, say the upper or lower split or the upper and lower level of this band, it's a function not just of the coupling, but it's also of which level, which harmonic level is being split or being perturbed. So there's a formal series in H-bar with coefficients that are explicit functions, in fact, polynomials in this band or label. And then there's the exponentially small splitting due to the instanton. And then there's a fluctuation around the instanton. And then there's a second order instanton and so on. What I said on the previous slide was that the coefficients of the imaginary part in the second order effect are related to the perturbative ones. But in fact, it's even more explicit than that. Even these coefficients here of the one instanton effect can be written in absolutely closed form in terms of the perturbative coefficients. And in fact, it's not just true of these. At any order in the this trans series expansion, the fluctuation coefficients can be written in terms of just the perturbative coefficients. So this is very interesting and very surprising. This is actually an example of this resurgent structure where we now have an infinite number of saddles, and we're able to characterize the fluctuations around any one of them in terms of the fluctuations around one of them, namely the simplest one, the perturbative saddle. So that's quite surprising. And in fact, I would argue that people wouldn't have looked for these relations without having thought about this problem through the lens of resurgence. But again, that's just one parameter here, that we're talking about expansions in just one parameter H-bar. But in general, we'll be interested in many parameters. We might be interested in introducing masses, couplings, chemical potential, temperature. And so we need to understand that. And here, physicists are really on their own because there's very little work in the mathematical literature about multiple parameter expansions. But one particular example that we would like to understand is something like a phase transition, where we introduce some parameter where we could think of a thermodynamic limit in which we might be able to construct a situation where there's a phase transition in the other parameter. So for example, we could consider a 't Hooft limit where n goes to infinity, the coupling goes to 0, but the product remains fixed, but that product could be small or large. And there could be a phase transition between the small or large regime of this 't Hooft coupling. And something very interesting happens to these transeries. They actually transmute as you cross one of these phase transitions, and they turn into a completely different structure of a transeries. And this is a real nonlinear and infinite dimensional version of these Stokes transitions. So we can actually see this effect already in this periodic potential problem. So here I'm plotting the spectrum. So the energy as a function of h bar, here's the Schrodinger equation. And n here labels which band I'm talking about. So this is the n equals 0 band, n equals 1, 2, 3, etc. Or it could label a gap. So here's the potential. It's going cosine potential going between -1 and 1 on this energy scale. And we see indeed that low down inside a well, we've got bands that are exponentially narrow. But as you go up towards the top of the barrier, these bands widen and become not exponentially narrow. Whereas way above the potential, we've got these very narrow gaps in the spectrum. And we know from basic solid state physics that we describe this physics here using a completely different terminology from how we describe the system here. Here we use the tight binding approximation, and here we use the nearly free electron model. But this is actually a genuine phase transition between narrow bands and narrow gaps. If you look very closely near this top of the barrier, you'll see that the band width is equal to the gap width. The band width is equal to the gap width, and so on. And so near this top of the barrier, there's a genuine phase transition in this n goes to infinity limit. And with this normalization, it happens when this 't Hooft coupling is 8/pi. Moreover, it's a transition between real instantons and complex instantons. Because while we're all familiar with the fact that real instantons tunneling between real turning points here govern the width of these bands, what may be less familiar to people is a result in the solid state literature that up here where there are only complex turning points, integrating between these complex turning points and exponentiating actually gives you the width of these gaps in the spectrum. So this transition is actually a Stokes transition where the physics is dominated by real instantons and then by complex instantons. In fact, as you approach this transition, the one instanton approximation is not sufficient. You have to somehow resum all orders of the transeries. So when we come to quantum field theory, of course, things are much more complicated. And yet I can show you now an example, which is very, very similar to that quantum mechanical example. And this, I think, is clearly the first calculation in quantum field theory to display this type of behavior by Heisenberg and his student Euler in the mid-1930s, where they did a calculation which we would now call effective field theory. So this is electrons and positrons in the presence of an electromagnetic field. So the philosophy of Euler in his thesis was to integrate out the heavy degrees of freedom, which are the electrons and positrons, and compute, therefore, an effective field theory, an effective Lagrangian, which describes the interactions of the low energy degrees of freedom, which here are the photons, the electromagnetic fields. So in modern terminology, this would be a perturbative calculation of these Feynman diagrams, one loop diagrams, in a constant background electromagnetic field. Of course, that's not how they did the calculation. They used the exact propagator in a constant electromagnetic field, and then the expansion gives you this perturbative expansion. They were able to calculate the full non-perturbative calculation. It's a spectacular calculation. And this integral representation here is actually exactly the Borel sum of what you would get if you did this perturbative calculation. And in the presence of an electric field, there is indeed an imaginary part to this effective Lagrangian associated with particle production in a background electromagnetic electric field from the quantum vacuum. This is a very close analog of the Stark effect ionization thing that I described before, and of Dyson's instability in QED. Now we can generalize this to a case where it's not just a constant electric field, but a monochromatic electric field. So we introduce a new parameter, a frequency. So the electric field is characterized by a magnitude and a frequency omega. So 2 parameters now instead of 1. So this problem was solved by Keldysh in the early 1960s, shortly after the introduction of lasers, motivated by the ionization problem in atomic physics. It was then generalized to the QED situation by Brezan and Itzikson. It was actually Brezan's PhD thesis, and independently by Popov at roughly the same time. And the key parameter is this Tuft-like parameter, this Keldysh adiabaticity parameter, which is a ratio of the frequency in units set by the scale of the strength of the electric field and the mass scale. So a WKB calculation done by these people gives you that the leading exponential part of the rate of pair production due to this now time-dependent electric field has this familiar Euler-Heisenberg factor here, multiplied by some function of gamma. It's an explicit elliptic integral expression, not that important exactly what it looks like. But the important thing is that when gamma is small, where you go back to the constant field approximation, you reproduce the Euler-Heisenberg exponential. And so that can be viewed as tunneling pair production or tunneling ionization. But in the opposite limit, where gamma is large, this function develops a logarithmic behavior. And now you have an exponential of a logarithm. And when all the dust settles, it's actually a perturbative expression in the external field. So this is basically the vector potential corresponding to this background field. And the power here we recognize as twice, because it's a probability, the binding energy of these electron-positron pairs, which is 2mc squared, divided by the photon energy. So this can be interpreted as now multi-photon ionizational pair production. And the transition between these two, as you vary this Tuft-like parameter, is a genuine phase transition. And it's a phase transition where the physics is either governed by real or complex instantons. And actually, this is the context in which I first learned about resurgence and was trying to use resurgence to explain this type of physics. And it turns out this transition is very, very similar to the transition I described in this quantum mechanical periodic potential problem. With this extra parameter, whereas in the Euler-Heisenberg case, the Borel transform is a simple meromorphic function with simple singularities, with the introduction of this extra frequency parameter, that's no longer true. It's a much richer Borel transform structure. Interesting, I'd like to point out that there are genuine and well-advanced experimental proposals, both at SLAC and at DAISY, to do experiments using very high-intensity lasers interacting with high-energy electron beams to probe this transition region. Because it turns out that the very high-intensity region of field theory, and for even QED, has not been explored in any controlled experimental way. It's an uncharted territory in quantum field theory. Very, very different from the high energy regime is the high intensity regime. I think in the interests of time, I'm going to have to skip this or go through it very quickly. One way to see how this relates to the path integral is that we can use the Feynman world line representation, this sort of first quantized expression of the effective action as a log determinant or a trace log. And we express the trace of the heat kernel as a quantum mechanical path integral over trajectories in Minkowski space parameterized by proper time. And now it's a double saddle point calculation to do a semi-classical calculation. You first make a semi-classical approximation to this now 4-dimensional quantum mechanical relativistic path integral, but then you're confronted with also doing this proper time integral. And this is very similar in strategy to what Gutzwiller developed in the context of atomic physics and quantum chaos. And the net result is that we learn that in background fields that are inhomogeneous and very localized and very intense, they necessarily involve complex saddles of the path integral, this world line path integral. And we learned that particle production, these non-perturbative effects related to particle production are genuine examples of Stokes phenomenon. And you can actually take advantage of that once you understand that to design and optimize the form of laser pulses, for example, that might be used to maximize these nonlinear interference effects. So that's one of my main physical motivations of why I'm interested in this question of resurgence and path integrals. Now, a very explicit example of phase transitions in not quite functional integrals, but in baby versions of quantum field theory, is this beautiful Gross-Witten-Waddell unitary matrix model, which is a model of two-dimensional lattice gauge theory, which reduces to an integral over n by n unitary matrices. And the action is some generalization of the cosine function, u plus u dagger. And so there's an n parameter for the n by n unitary matrices, and then a 't Hooft coupling parameter t. And the discovery of Gross and Witten and of Waddell was that there's a third order phase transition at some fixed value of this coupling parameter t. So this partition function depends explicitly on two parameters, not just one. Using some magic properties of random matrices and orthogonal polynomials, you can actually do all these integrals and reduce the partition function to an n by n determinant whose entries are just modified Bessel functions. So this is a very explicit representation. But unfortunately, determinants are not very friendly to large n limits. They're very clumsy at large n. And there turns out to be a more practical way to develop the trans series. So first of all, I forgot to mention, here's a plot from the paper of Gross and Witten showing this kink-like behavior at n equals infinity in the specific heat. And their normalization was slightly different. It's happening at 2 instead of at 1. I've normalized things so that the transition is at 1. Now, an easy way to develop this trans series is to use this result of Rossi from the early 1980s, that it's not quite an order parameter, but the expectation value of the determinant of this unitary matrix satisfies a nonlinear differential equation, where these primes here refer to derivatives with respect to this 't Hooft parameter t. And you see that the n of the n by n unitary matrices just enters as coefficients of this differential equation. So the resurgence story for such differential equations is extremely well developed and very easy to implement. And one can use this to develop the trans series at weak coupling and also at strong coupling and understand how they're related to one another. So it's simply a matter of inserting an ansatz like this with an expansion in inverse powers of n with some coefficients that are manifestly functions of the other variable t, inserting it into the differential equation, expanding and matching powers of n. Trivial calculation to generate these coefficients, even though they're functions of t. And no big surprise, you learn that for the small values of t, these coefficients grow factorially in magnitude, which tells you you should upgrade this series to a trans series by introducing some exponentially small term, also multiplied by an expansion. Now you insert this more general ansatz into the differential equation, again expand, and you immediately learn that this action here is some very specific function of t. And also the prefactor has this familiar WKB type structure in terms of this function. It's also easy to then generate the coefficients of this, let's call it the one instant time fluctuation term. And you can go higher into the trans series and recursively generate it. Very, very, very simple type of calculation using something like Mathematica or Maple. And now Resurgence shows up, and we can actually study the large order growth of these coefficients. And indeed, it is factorial, gamma 2n minus a very specific offset. But it involves explicitly this action function here, which is this location of the Borel singularity, which remember moves around as a function of t. So it's kind of interesting if you just had this formal series, the large order growth of this immediately tells you about this function here, even if you didn't know the differential equation. Moreover, the subleading corrections to the leading factorial growth have a particular coefficient, which again matches with the next coefficient of the fluctuations around this one incident term, and so on. You can consider this at higher and higher orders in the trans series expansion. This is an extremely explicit example. Now you can look at strong coupling. We can look at this differential equation in the regime where t is large, and the trans series that's developed there is completely different in structure. It turns out the leading solution is actually just a Bessel function, where n appears as the index, but also in the argument. So the large n limit is one of these correlated limits. It's called a Debye expansion. And the leading behavior is exponential. There's no pure fluctuation term. There's just immediately a non-perturbative behavior. So it's a little bit like the Airy case. There's immediately an exponential decay. And likewise, you can generate the fluctuations around that. You discover that the next instant on order is actually only the odd powers of this exponential factor show up. And you can generate a trans series. This action on the strong coupling side follows immediately from inserting this ansatz into the differential equation. And there are these large order, low order resurgence relations also. The main point is that that I want to make here is that the trans series on one side of the phase transition and on the other side of this phase transition are completely different from one another. As you approach the phase transition, you need all the terms in the trans series, and as they merge, they transmute into one another in a so-called double scaling regime. So if we rescale the variable around, look at the deviation from the phase transition point with a very specific scaling of the large N parameter, which is related to the scaling in the statistical physics sense. In this regime, that differential equation, that Rossi equation, reduces to something called the Painlevé-2 equation, which is really the nonlinear version of the Airy equation. So this is very similar to what we're completely familiar with in quantum mechanics, where if we viewed this as a turning point, on one side of the turning point, we might have oscillatory behavior of the wave function. And on the other side, we might have exponential decay of the wave function. And in order to match these two together, we use this intermediate regime in which it's an Airy function, which on one side has the exponential decay, on the other side, the oscillatory decay. And this example is quite literally a nonlinear version of that phenomenon. And that's why this Gross-Witten-Poitier unitary matrix model is so universal in many problems in physics, but also in mathematics, is describing these sorts of Stokes transitions and these large N models. We also learn an interesting Li-Yang interpretation here, is that at finite values of N, this partition function is just a large determinant with entries that are just Bessel functions. So it has some zeros, they're complex, but in the large N limit, they actually pinch, this is the philosophy of Li and Yang, they should pinch the real t-axis at the location of the phase transition. And indeed, that's exactly what happens. Here's an image of the zeros of the partition function in this transition region for this nonlinear area equation. And these ones here just pinch exactly at the transition point. This is a deviation from 1, with exactly the right scaling behavior with N. This is a very beautiful example of resurgence in one of these matrix models. So to conclude, I want to make a few comments about another approach where instead of starting from the functional integral and developing the trans series, there are other problems where you might have an expansion and it's not even obvious how it came directly from a path integral. It may have been developed through a much more complicated series of maneuvers. And so there's a question of whether you can actually use ideas from resurgence to somehow rebuild the trans series just from perturbative information. So this is some work I've been doing recently with a mathematician, Ovidiu Costin, who's an expert on these, on resurgence and asymptotics, because there are some genuinely difficult problems in physics where we're only able to use perturbation theory to calculate some very limited number of coefficients in an expansion. And sometimes that's just the only thing we can do. And so if we take resurgence seriously, you would think that maybe using these ideas, we can develop improved methods of extrapolation, because resurgence tells us that there should be some connection between the expansion in the region we're trying to do something and some other region that we might be interested in. For example, physically, here's a sketch of the anticipated phase diagram in QCD as a function of temperature and chemical potential. And there's a lot of activity centered these days around identifying this, both theoretically and experimentally, this critical point, which is anticipated at the end of this first order line. However, doing calculations analytically or even numerically in this regime is extremely difficult. So it's reasonable to ask the question, if you were to do a calculation in a regime where you have better control over a calculation, can you somehow use these ideas from Resurgence to enable you to extrapolate from a distant regime from where you're interested in, but from a regime where you can actually do something? And if so, how many terms do you need in an expansion? So here's a very explicit example. There's this another one of these interesting nonlinear differential equations that keeps showing up in physics applications is Penove-1 equation. It has this interesting five-fold structure in the complex variable plane. And if you develop an asymptotic expansion around the large X, large positive X regime, you can ask, does that perturbative expansion contain enough information to cross this nonlinear Stokes transition and another nonlinear Stokes transition into a regime where the function has a completely different structure? It has a series of poles, whereas there are no poles in any of these other sectors. And the answer surprisingly turns out to be yes. There are very clear methods that you can develop for extrapolating, taking advantage of resurgent ideas that will enable you from a very small number of, a surprisingly small number of coefficients in some regime here, to go into a completely different Stokes sector. Let me just show you one physics example. That's the last thing. Going back to this Euler-Heisenberg example, at one loop, the effective Lagrangian, if we restrict to just having a magnetic field, there's a very explicit integral representation. Here's the Borel transform. It just has poles equally spaced along the imaginary axis, a very simple Borel structure. The weak field expansion, weak magnetic field expansion is here. It's factorially divergent, alternating as we expect. The strong magnetic field limit is defined by this b squared log b behavior, and the coefficient is the first beta function coefficient in QED. So we can ask, suppose the only thing we could do was to calculate a few terms of this weak field expansion. Is that enough information to extract this strong field behavior? And is it enough information also to go into the complex plane and analytically continue from B to I times B, which would be now an electric field, where there should now be pair production due to the constant electric field? So surprisingly, you can develop extrapolation methods and analytic continuation methods where with just 10 terms of this weak magnetic field calculation, you can match smoothly over here 7 orders of magnitude into the strong field regime. And you can identify the 1/3, the QED beta function, just from 10 terms of this weak field expansion. It's very surprising. That number could have turned out to be 100, and it's just something of the order of 10. Even more surprising is that you can take just those 10 terms, develop extrapolations and analytic continuations of the Borel transform, and over 3 orders of magnitude here, extremely accurate continuations to the exponentially suppressed imaginary part of the effective Lagrangian in the electric field. Again, I was very surprised by these, that it was such a small number. And it's not just a feature of one loop. At 2 loop, there's a heroic calculation by Ritas from back in the 1970s, which results in a very complicated double integral representation, not a Borel integral representation, but which you can expand to some certain order. And now you can use exactly the same strategy of just rebuilding the trans series from a finite number of terms in this series. And again, you can extrapolate over many, many orders of magnitude just from this initial perturbative information. So this is the philosophy of starting with perturbation theory, rebuilding the trans series. And this should correspond to starting at the other end, starting with the path integral and generating either the perturbative series or going directly to the trans series from a saddle point or a thimble calculation. Okay, I've come to the end, so let me conclude. I think the overall message is that Resurgence is based on a new and improved form of asymptotics from the mathematics literature. Applications in physics so far have led to even deeper connections between perturbative and non-perturbative physics, even deeper than the ones that were already understood. This came from developments in differential equations and dynamical systems in mathematics, but it's now been applied in many examples in quantum mechanics, matrix models, certain quantum field theories, and certain string theories. And so far it's survived the tests. And it's by no means clear that at the formal level, this should apply in the generalized application to infinite dimensional functional integrals. But there's been a lot of activity of just exploring how it works in certain models, and so far the results have been quite encouraging. And then I mentioned at the end here this idea of resurgent extrapolation, that surprisingly high precision extrapolations can be developed, extrapolation techniques can be developed using some of these ideas. So I would hope that the outlook is that some of this activity continues and gives us new ways of calculating the path integral, both from the point of view of lattice gauge theory, but also semi-classical expansions, large N expansions, to have now genuine controllable computational access to strongly coupled systems, finite density systems, phase transitions in strongly coupled systems, particle production and related non-perturbative effects, back reaction effects, non-equilibrium physics, things that are currently difficult to study using path integrals without using very specialized techniques for different design for each system independently. Now, there's a lot of activity going on here, and there are many things that I didn't talk about today. I just list them here, things that if you're interested in, you can investigate. All right, thank you.
Thank you very much, Gerald, for this very, very nice talk and overview. So now we have time for some questions. I would ask, I already see some raised hands. So maybe I will just call you. I also wanted to ask maybe a quick question before giving the floor to the people that have asked. So I abuse my prerogative a little bit. About your last example, which I found particularly striking, about the Euler-Heisenberg example, and how you can reconstruct just from a handful of terms the behavior of the function. Now, is there a general understanding of how many terms are enough? I mean, if you don't have any other way to cross-check, and you try to extrapolate, you have a few coefficients, a few terms, and you try to extrapolate the function there. Can you tell a priori in general how well you're doing, how far you need to go in order to get something sensible?
So the short answer is yes, but the long answer is long. So yes, there are ways. So you can characterize the number of terms you need to achieve a certain precision, but you can also reverse that and say, given a certain number of terms, you can actually work out what level of precision you can attain. And the reason you can do these calculations is that in physics applications, it's this generic structure that typically the large order growth of perturbative coefficients typically has a generic form of factorial with some powers as the leading structure. And if you take that as the leading structure and use these ideas of resurgence, you can actually do very precise estimates of what, and you can even estimate that if you were to do this method of processing the information, you would get this level of precision. If you were to apply another level of analysis, you would improve it by this much as a function of n. But that's understood. A deeper and more, I think, more interesting question, where there are also partial results so far, is in really hard problems, we don't actually know the coefficients exactly. We may only know them to a certain level of precision. And even that question, there are generic things that you can say about the relation between the level of precision, let's say the number of digits, for example, and the number of terms beyond. If you take too many terms with only a finite amount of precision, I can tell you when it's going to bomb. So there's a very rich structure. It's not fully explored, but there's genuine universality there. Within this world of generic factorial growth, which seems to be characteristic of most, if not all, physics problems.
So I think in the meantime, thank you very much. In the meantime, both Arkady and David have questions. Let's start with Arkady, perhaps.
Okay. Thanks for the talk, Gerald. But my question is about the topic which mentioned in your conclusion as in Malon's and operator product expansion. So my impression is that we're reacting that your example will say electric field are example where you in certain sense you have additional information, right, when to define physical function, because say that it is ionization or whatever, right? So there is this something which is not, I mean, and it's associated with this non-summable sum. Well, you have the same sign, in factorial divergences. Malons are special in a sense that they are not in quantum mechanics. So in this way, but they are the same problem. For example, when we are talking about, say, infrared Malons in QCD, you have this non-alternating sign, right? My question is related that could be that, say, appearance of additional stuff like condensate, which are associated with these Malons, could be analog of your imaginary part in ionization. So I mean, I just wonder, because it could be special status of this phenomena. In 5 to the 4th theory, it would be kind of UV ultraviolet Malons, right? And again, it is a question about 1 over Q power corrections in certain sense there. So it's my question.
Yeah. Okay. Well, this would be a very long discussion for the answer. But I think we can all agree that the operator product expansion has the general structure of something like a trans series, right? A combination of non-perturbative information and perturbative fluctuation. In my opinion, this is not yet fully understood to a satisfactory level for infrared renormals. There's been a lot of work on this, and there are actually some very interesting results from Marcos Mourinho and company recently looking at certain special models where you can use extra tools of integrability to probe to very high precision. So I don't think it's settled yet. This is clearly a very important problem listed here in Yang-Mills and pH.D, where we don't understand in enough detail, and where there hasn't been the level of numerical path integral contribution that we would like. So.
Okay, so I should wait, right?
Yeah, we'll continue our conversation maybe for many years, who knows. But that's one of the main motivating examples, and to try and understand that. So.
Great, I think David now has a question.
Yes, my question concerns the four-dimensional quantum field theory, for which we have the largest amount of perturbative information, yes, namely 5 to the 4th theory in 4 dimensions.
Yes.
And thanks to heroic work by Eric Panzer and Oliver Schnetz, we now know exactly the 6 and 7 loop coefficients of the minimalist attractive beta function. But Eric and Mishi Berinsky have been developing really very interesting methods to estimate maybe terms as high as 11 loops. So is that enough for you to be able to say something about the asymptotics of the beta function of 5 to the 4th theory?
Well, this is a bit of a leading question, I guess, because just posted a paper speculating about this yesterday. So I would argue that the answer is yes, but I think the more important point here to emphasize to people is that there have been recent developments over the last 10 to 15 years of extremely powerful techniques to do high orders of perturbation theory, not just using the brute force Feynman diagram approach, but of systematizing this and using all sorts of hidden structure that's not obvious from the immediate path integral. And we're now at the point where these new techniques are developed to the level where they can actually seriously discuss doing 11 loop calculations, 20 loop calculations. And now the discussion gets interesting, because if you can do 4 or 5 loop calculations, and these are massively serious and impressive calculations to do 4 or 5 loop calculations, but that's not quite enough to be able to get to this testing, probing these large order growth regimes. But this example that I showed in the Euler-Heisenberg case, there's some sort of threshold somewhere between 10 and 20 with generic factorial growth. We can really start to do something with that much perturbative information. And I'm actually very excited by the fact that these developments in the amplitude world and using these Hopf algebra methods and these number theoretic methods have been able to get to do genuine perturbative calculations in really non-trivial field theories to extremely high order. And I think we're on the verge of being able to combine these two. It's not quite there yet, but in 5-4 theory, there's a lot of information now. And I think it's time to start taking this seriously. Because maybe one can go in the other direction. And from these perturbative calculations, step towards at least ask these questions of whether one can.
I have a historical remark from 40 years ago where Xinjia Stan gave some inspiring lectures at St. Andrews. And when asked to pull out of the air a figure for how many loops was enough, his answer was 12.
Interesting. Foresight. The usual answer is one's not enough and 100's too many. So
I think we have a couple more questions. First from Marco Gualtieri and then from Lance Dixon. So Marco, please.
Hi, Marco.
Hi, thank you for your beautiful talk. I just wanted to ask a really elementary question, but about something that maybe was implicit in everything that you've been saying, which is that when you are able to go from the perturbation theory and make conclusions about non-perturbative effects, there's a kind of implicit assumption that the theory that you're talking about is actually non-perturbatively well-defined.
Yes, so this is one of the underlying unknowns,
right?
Which makes this problem interesting, an interesting realm in which to study these train series. Does it actually, does it define a unique non-perturbative definition of the theory?
Right.
And I don't
so
think,
I've often, oh, I'm sorry. So
no,
I've often heard physicists say that quantum electrodynamics should not be expected to be non-perturbatively well-defined. Do you think that's true, or how does that fit into what you've been studying?
Well, there's this, so this would also be a long discussion. So it's not asymptotically free, so there's a problem in the ultraviolet. Whether we will be able to say that the standard model is non-perturbatively complete, that's just beyond what we can even dream of doing now. But I think studying these sorts of questions, even in integrable models, is really a fascinating question, because there you have much more control over the non-perturbative side of things, and even learning whether there is a unique non-perturbative definition or non-perturbative completion of integrable systems where you have total control. Even that's an interesting question before you get to something more physical like QED or QCD or Yang-Mills. I don't think there's an answer. And with QED, I think we need more information than you would be able to develop from perturbation theory, but maybe it's encoded somewhere in the perturbation theory. Who knows?
So I think Lance, sorry. I just wanted to invite Lance, who is apparently on the move, to ask the next question.
Yeah, thanks for that fascinating talk, Gerald. I just wanted to mention that there's another 4D QFT where there's perturbative data up to 7 or 8 loops as a function of multiple parameters, which is n equals 4 super Yang-Mills in the large n limit. Now, in this case, the perturbative expansion seems likely to be completely convergent because instantons are exponentially suppressed as n goes to infinity and there are no renormalons. So what would you say? Maybe it's just too simple for your consideration.
So actually, I'm very glad you asked that question, because there's a widespread impression that this resurgent story only applies to divergent series, and that's actually not true. It applies also to convergent series. So a very explicit example of this, which is actually very important in many quantum field theories, is the so-called Penave-6 equation, which is underlying the physics of for example, even the Ising model. And this is sort of the mother of all integrable models. Penave-6 can reduce to the other Penave systems. But the Penave-6 expansions, there are 3 expansion points, say 0, 1, and infinity, and all the expansions are convergent. Okay, and yet they have, this is only very recent work by Lisovi and Gamillon and company, maybe 10 years ago or less. These expansions in Penave-6 can be written explicitly in terms of conformal block expansions in total closed form. And when you look at them that way, for something called the tau function in Penave-6, this is really spectacular in my opinion. When you look at them that way, you get an expansion, a double expansion, which looks just like an instanton expansion, even though everything's completely convergent in the sense, so it's not only divergent series that have this trans-series structure. And maybe a less fancy version, go back to the periodic potential problem, right? So if you calculate the energies of bands, bound bands, the expansions are divergent, and we use instantons to dress them up to get these exponentially small splittings. But now you go look up in a table of integrals, look at the expressions for the gap edges high up in the spectrum. They're all convergent. Okay, they have a finite radius of convergence. The radius of convergence depends on which gap you're talking about, but they're all finite. And yet, this resurgent structure that I talked about, the relation between the one instanton fluctuations and the perturbative expansion, exactly the same relation holds for those gap expansions, even though they're completely convergent. Okay, so there's a really rich structure here. Another way to say the same thing is that if you have a divergent series for a function that's resurgent, well, you can just turn it into a convergent problem by taking the Borel transform. And so the resurgent relations of the function boil down to resurgent relations of the Borel transform, obviously. And so if you just make the discussion at the level of the Borel transform, you're just dealing with convergent series. So I want to make this clear that resurgence is not just a feature of divergent series. It's much more general than that.
Great, thanks a lot.
Yeah, so this would actually be a very beautiful example, this n equals 4 case. So, yeah.
All right, are there any more questions or comments?
So I thought concerning Lance's remark, if you look to perturbation theory from the strong coupling side of n equal 4 for Yang-Mills, I thought that was asymptotic.
Yeah, that's right. From the weak coupling side, it's convergent. Usually,
Yeah,
the strong coupling is asymptotic.
Yeah, yeah, there are, and indeed, yeah, it must be related to sigma model from the strong coupling sides, I presume, and that asymptotic behavior must be related to the perturbation theory of some sigma model, and it must be related to, again, to the renormalon problem somehow. But there are a number of physical problems in which on one side we have an asymptotic expansion, and on the other side we have a, some convergent expansion.
Yeah, there are many physical examples where it's divergent on one side, convergent on the other, or convergent and divergent and divergent. So.
All right, so if there are no more questions or comments, also in view of time, I would suggest that we thank again Gerald for the nice talk and answering all the questions very nicely. And I'll give the floor back to Stefania at this point.
difference.
Just to thank also from my side for this beautiful seminar, and to thank all of you who attended the GGI Tea Breaks seminars, and give you the appointment for the next week.